Dr. Juan Wachs is a professor and faculty scholar in the Industrial Engineering School at Purdue University, professor of biomedical engineering by courtesy, and an adjunct associate professor of surgery at the IU School of Medicine. He is currently serving as NSF program director for Robotics, so the FRR program, and the AI programs at SAIS. He is also the director of the Intelligent Systems and Assistive Technologies Lab at Purdue, and he is affiliated with the Regent's Center for Healthcare Engineering. He completed his postdoctoral training at the Naval Postgraduate School's MOVES Institute under a National Research Council Fellowship from the National Academies of Science, and that's something that I identify with because I also had one of those fellowships. They were very good. And I guess for people in the U.S., know that is a good postdoc fellowship that you can apply for. So he received his PhD in industrial engineering and management from Ben Gurion University in Israel. He is a recipient of the Air Force Young Investigator Award, the Helmsley Senior Scientist Fellow, and a 2016 Fulbright U.S. Scholar, among other honors and awards. So I am very happy that Dr. Juan Wachs is here to talk to us about his research. And I'm going to pass the microphone to you.
Thank you. So let's see. Can you hear me okay? All right. Well, let's get started. Thank you so much, Michael, for the invitation and for the introduction. And I'm glad to be here. And I appreciate that you guys came here. Friday, and you have a big game today. So I hope that you enjoy the talk. Please feel free to ask questions anytime. I enjoy when it's more participatory. So I wanted to start by giving a picture, motivating the talk by looking at how surgery was done in the past. What you have here is a painting from the 19th century of the surgical theater. Surgical theater, the operating room is called surgical theater. Why is it called surgical theater? Because it was done in a theater. And of course, the residents, students, and the teachers were all around the patient, performing. In this case, they are doing an anatomy on a cadaver, and this is how they would be teaching surgery to large crowds all around, all trying to figure out what's going on and receiving explanations from the expert. Only 10 years after that, practices change drastically, dramatically, due to the understanding of infections and the spread of infections, and the understanding that actually the humans are the main factor of the spread of infections. In this case, why? Because they are wearing different clothes. They are using white gowns that are different attires from the everyday clothes. But so they no gloves. Not still no gloves, right? And the reason is again a cadaver, but still hands are a factor of spread. They understood that these white gowns are very helpful in to be able to see the contrast of colors and to see body fluids and for example, and blood. So they realized that practices have been changing since that time, even earlier, and we kept, in fact, doing progress, making progress in medicine up to these days, where when you look at a modern operating room, it's machines, devices, monitors all around. In fact, where is the patient here? Right? Where is the patient? I like this analysis. So things change up to the point that the location is not longer about blood and guts, but it's about bits and bytes, right? I like this cartoon. This shows you what I was telling you. Where is the patient, right? The patient is somewhere there, but no one is really paying attention to the patient. Everybody is. Surgeons are engaged with machines, robots, and monitors, and the human touch is lost. We wonder, where is the human in this process? How we can bring the human back to this process? And when we look into where the human is in this process, we ask the questions, or we look into challenges that deal with, we don't really know how to make robots and humans work together effectively. especially when robots are holding knives, scalpels, right? I think that Rodney Brooks was someone that said, don't give knives to robots, right? They have guns and they have bombs, don't give knives. We don't really know how to convey the sense of presence when teleoperating robots, especially surgical robots. And, medicine is all about transferring the know-how for centuries. How that is applicable to a new configuration, a new setting where you do surgery with robots. Robotic surgery is very different. So can we transfer, how we can transfer actually this knowledge? It's a significant challenge. So I'm going to try to answer these questions through a number of projects that we found interesting and compelling, and we thought that solving or completing these projects are going to provide solution to some of these questions. So the first one is the STAR platform, which is telemedicine platform using augmented reality. This was in collaboration with IU School of Medicine, the Army, and TATRIC, which is a branch of the Department of Defense dealing with telemedicine. And well, so here's the question, right? You don't always have the expertise that you need in the place that you need. So if you're looking, for example, in an improvised hospital in Haiti or in a conflict region in Afghanistan, for giving one example, and you have, for example, a traumatic brain injury, and you need an expert, you need a neurosurgeon, the neurosurgeon may not be around you when you need it, right? You only have a bunch of surgeons and clinicians around you. So the question is there a way to optimize the treatment from experts when they are not available in the same location? Let me motivate the research through this little video.
All right, let's make sure the area is clear. Nurse, I'm coming in with a blast injury. Right shin swelling quickly.
I'll prep him for surgery.
He could lose his leg.
We can contact our mentor stateside.
Hello, this is Dr. Andrews. How can I help?
My patient was caught in an IED blast. His shin is swelling, and he seems to be in danger of developing compartment syndrome.
We need to do a fasciotomy. Don't worry, I'll walk you through everything.
He's ready for surgery.
Send me the data. We'll make 2 incisions. The lateral incision will be made halfway between the tibia crest and the fibula. Incise along this line.
So here you see annotations that are drawn on the large interaction table and this projection on the
Now
tablet.
we'll make an H shape and use scissors to cut the fascia.
Let me skip all this. So basically you have a medic or surgeon following instructions, and eventually, of course, they save the patient.
But you need to have a simulator for this, right? So that you can do things on the screen that are like...
Right, a model or a simulated model, right. So this is basically the architecture, right? So in the top left, you have the mentor side with a large interaction screen, a projection of the patient, which is a virtual patient. This is what we call the simulation. And the expert around the table are providing annotations and putting surgical tools, eventually telling the medic or the trainee what needs to happen. This information is transferred remotely to the medic or trainee, where these annotations are generated on a see-through display, which allows you also to have the capability of going backward and forward. Here you have a view, you have virtual instruments, annotations, and real instruments. And here the trainee, medic, resident, doesn't matter. What they do is they follow the instructions that they receive through the using this display. And so we tried this in a very interesting class called Atom course in IU School of Medicine. What is this Atom class? So this is what they teach trauma surgery in IU School of Medicine. They have 4 stations, 4 tables, 4 pigs laying down, in automatic respiration. They have 4 experts, surgeon experts, and they call residents in. Now, every pig has a script associated with it. Means this is a patient, 20 years old, has an injury, blast injury on the leg or on the chest. We don't know what's going on, operate. So what the resident sees, in the beginning they don't see much. They need to start opening and then they see bleeding. So, okay, something's going wrong. They need to fix the patient. And of course, the experts are silent and they look at what the residents are doing, how long it takes them to fix them. And of course, once they succeed, eventually they tell them, okay, you can go out. And they create another script on the same pig, another scenario, and eventually, and they call back the resident and say, well, now there's something else. They give the script, and again, they need to fix the pig. Okay, it's the same pig, right? Eventually, the last time that they call them is because there is a blast injury, a bullet on the heart. So when the residents come, what they see is blood spotting out in magnitudes, in quantities, and residents eventually need to fix, they need to suture an artery on the heart itself. There is a lot of stress. I can tell you that. But I'm telling all this because this gives us an excellent opportunity to operate on the porcine model once the class is over, because eventually they will have to euthanize this pig, right? So we thought about using or doing a fasciotomy on the pig, having a resident perform a fasciotomy on the pig using this system. Now, this is a very bulky system. It's the first prototype of the telementoring system. And we tried that on the Adjunct class. And here you have the chief trauma surgeon from IU School of Medicine, Jerry Gomez, giving instructions.
Can you see my arrows? Yes. Can you cut from the tip of the arrow to the next tip of the arrow? Yeah.
And he was following the instructions and completing the fasciotomy. And then we said, well, how are they actually going to interact as a group? How they're going to interact with a large interaction table? How they're going to interact as a group? And at what extent they use surgical instruments? At what extent they use annotations? And we wanted to make sure that we create the necessary algorithms and technology to convert all this information into cues in augmented reality that are generated on the tablet. Now, one of the challenges, one of the first type of feedback that we received is that the tablet was a very bad model because it was interfering with the use of the hands and arms, which is what the surgeons do, is they use their hands. So we have to actually change that. We move into a HoloLens type of concept. And here is basically the same fasciotomy performed by an expert that is giving instructions while the expert is generating the annotations. The medics are getting the annotations generated on the augmented reality display and performing the annotations. So, by the way, I was telling Michael that when I presented this to undergraduates, I cut the image here to make sure that they don't know if there is a body here, or because it's a leg, it's a cadaveric leg. But I forgot to take care of this image. So here you actually see that the leg is actually chopped. Sorry. Okay, I tried. Anyway, so, all right. Now, all good and nice. Yes?
What is the surgery that's being performed, the fasciotomy?
It's called fasciotomy. So they actually open the fascia and it's called compartment decompression. Okay. So they have compartment compression as a result of an impact, a strong impact on the leg that generates the compression, and you need to basically release the pressure by opening certain areas on the tissue. So there are 4 compartments, 2 in each side, and this is how they do that. So it's a procedure that they may need to have, may need to perform in the battlefield, as for example, as a result of stepping on a mine or close to a blast, to an explosion, to a mine. So now in the field, you don't really have the ability to stack a camera on surgical lights, right? There is no surgical lights. So we thought, how we're going to solve that problem? Well, this is where we can actually use robots, right? We can use drones that are going to be hovering on top of the patient. They're going to have a top view of the patient. They can zoom in a certain region, deliver the image to the expert. The expert can put the annotations on top of that, on that image, and those are going to be the pieces of information that the medic will receive to operate. And here are some little clips showing how this actually works. So you see, you have the medic operating on the patient, the drone hovering on top, the medic using the HoloLens. On the top right, you have a combination of virtual instruments and real instruments. They're following. And on the bottom right, you see the the expert generating these annotations. But here's a problem, right? If the application is going to be related to the Department of Defense and we have military applications, having a drone hovering on top of you is really bad because it's actually flagging on the position where you are. So can we get rid of that robot that actually we just brought in recently? Yes, we have to get rid of it. And one of the ways that we thought is, okay, let's use the camera that is on the HoloLens. Now, those are going to be the image that the experts are going to receive. But the problem is that the medic is not always looking at the patient. He's looking all around. And if you have explosions and you have gunshots or whatever, the medic is going to all look around. The images are going to be, moving, and that is going to create motion sickness. So we came up with a stabilization procedure using computer vision routines to make sure that the model is fixed. And it's only updated every time that you have changes on the views of the patient on a fixed regions. So that's how we perform this stabilization routine, which allow us to use the HoloLens and the cameras on the HoloLens. And what I'm going to show you is the last experiment that we did with this, which was a simulated field test of such a platform on an environment that recreates what it could be a field environment in the battlefield. So let me get going.
It's time now for the business of health, brought to you by Hendricks Regional Health. Well, a Purdue University researcher is taking the power of augmented reality to the battlefield. Business of Health reporter Kylie Valletta tells us how the project could save lives. Kylie.
Thank you, Gary. When soldiers are seriously wounded in battle and their injuries are beyond military medics' expertise, they often need to be airlifted or transported to the closest medical facility, typically taking several hours. Dr. Juan Wachs is an associate professor in the School of Industrial Engineering at Purdue. He joins me now to tell us about his technology that will help treat soldiers immediately after their injury.
So let me skip to the field test.
Responders are the people arriving to the place and required to give treatment immediately. Sometimes the procedures could be pretty simple, like cracks, opening the airways for the patient to breathe, but without the required knowledge and training and instructions, those
So they're performing a crack on a simulator. This is a simulator, but the idea here is that there is a lot of stressors around them, including an instructor that is screaming and shouting at them, "Go! We are losing him! Go! Go!" And they hear explosions, and the idea is how well they perform under these conditions.
Gary, back to you.
So let me see if we have this working out.
This was the local news channel.
That is, yes, of Indianapolis. So let me see if I can connect to the network and maybe able to show you this. This is not critical, but I forgot to connect. I don't know if I can connect. Can show you another use. Can I use this? Okay.
You can. You have to put your email address in. I haven't used it in years though, so I don't know if there's anything else required.
You may be able to use edu-ROM as well.
Or you want to access the internet?
Yeah. Oh, I need to.
Which one do we have? The room.
It's going to be only for. Do I need to, I guess, register?
Do you have edu-roam at Purdue?
I do.
Then you should be able to use edu-roam here.
Okay. Well, let me see. Is this allowing me to?
Maybe.
I guess I need to create a new account, and this is. Let's try this. This is not critical, this part, but yeah, because this is still not connecting. Okay, let's skip this. This is not critical. All right. So all this makes the basically relies on the assumption that I have a medic that I can send to the field and perform the life-saving skills to treat the patient. But what happens if you don't have a medic? Right, that's the first question. So one thing that we try to deal here is with that question, how we can actually use robots to deliver this treatment in the right place at the right time without having a medic going through the risks associated with the delivery of the care. So again, austere environments, this is challenging for medical personnel or anyone around, how we can actually use robots to deliver this treatment. Okay, that was a challenge. And here's the problem. The problem is, we ideally would like to equip a robot with a library of skills that we can deploy in real time. Now, to learn this library, you need data, right? And turns out that we have a lot of data from the operating room, for example, in settings like the Da Vinci robot. But we don't really have data that is coming from field robotics or field injuries, right? So we have a lot of Da Vinci type of data, but nothing really in field. So how we can actually learn the necessary skills to provide the treatment? That's the question. And the other question is how we deliver in real time instruction that can effectively, if you want, avoid the problem of delays, of telecommunication delays. So one thing that we thought about was, why don't we decouple the execution of the procedure on the robot side with the data annotation and the instruction side? So in this way, what we do is we let the remote surgeon or expert work on a simulation, but it's a realistic simulation that reflects exactly what's going on in the field, only keeping the essential elements. So in the moment that the instructions are generated, we compress this form of instructions into high-level knowledge, send them over to the robot decodes those instructions, and within the context of the environment, the patient and the anatomy of the patient, and performs the procedure. So again, here is, we have very little real data from the medical setting, from the field setting, but we have a lot of data from operating room using, for example, Da Vinci and simulations. And we can combine all this data and train machine learning algorithms to recognize these pieces of knowledge, high-level knowledge that we call that surgeons. This is a term that was coined by Gregory Hager and Johns Hopkins, who actually work with us in this project. So we basically, in order to obtain generalization, we try this with a bunch of different robots, some of them real robots, some of them simulations. We perform the same procedure several times, and we learn and we extract kinematic and visual information where we try to learn certain patterns associated with these surgeons. So in the moment that we recognize the surgeons, we only need to send the name of the surgeon or an index to the remote robot. The robot looks at the surgeon, looks at the context, decodes the surgeon, and performs the necessary maneuvers to complete the surgery.
So the surgeon is a special skill. A sequence of operations,
right,
something.
Right, exactly. Sequence of small actions, if you want, to be able to accomplish a task. But not only that, we wanted to be able to learn common patterns between robots and do transfer learning between the control environment of the operating room and the uncontrolled setting of the field. But what about learning from different surgeries? Can we learn from a peg and pull transfer and apply that to a surgical debridement? Surgical debridement is when you basically tear pieces of skin, for example, burn skin. This is a procedure that you need to perform, for example, in case of burn injuries, right? So this is what we did. So we actually check that if we use a machine learning model that is trained from scratch, right, and needs to receive observations to learn all the regimes necessary to complete the one, in this case, debridement, okay, from debridement. So we use a peg and pull to try to teach a debridement. If there is no peg and pull task at all, and we learn the debridement from scratch, you see that very few observations give you very few accuracy, which makes sense. And it takes over 60 observations to learn the skill. Where when we take a model that already performs the peg and pull transfer effectively, and we only provide a few observations on the debridement, we see with only very few observations, we can only reach almost, over 75% accuracy. And very soon we actually reach almost 85% accuracy, and this continues. So I just stopped it here, but you actually get quite over 90%. What is interesting here also is that what this is telling us is that we need little data. If we do this transfer learning, the amount of real data that you need, it can be very low to perform relatively well, which is the problem that we have with field information, field data. We have very little, it's scarce, right? So this is one of the nice outcomes of this work. But the other thing that we did is we also look into how challenging or how well we can deal with challenges. For example, in the peg and pull transfer, if we add to that a liquid, okay, a kind of turbulent regime of simulated blood, and this is not real blood, how well the computer vision techniques can deal with to recognize the different parts and being able to complete the peg and pull transfer. And for the debridement, well, we have the debridement task with a realistic, this is also simulation, but also a very realistic environment. Now, what you see here in yellow is, again, this is the display that the expert is using. Remember that this is a form of simulation that allows the surgeon to work in a decoupled manner, almost decoupled manner from the remote robot, but you still need to have an idea of what the robot is going to do next. So that what you see in yellow is the phantom model of what the robot actually, or what the robot is doing now, and the real model is what you see here with the colors of the robot, right? So you want really to minimize this error. Okay, but now I'm going to make things even more difficult. Yes?
Do you run into any sort of issues where, because the surgeon is maybe working from a different angle than they're normally used to, how like their movements might not have translated quite accurately to like a tabletop setting? Like, was there any, or was that not really a problem?
No, yes, and this is a setting that in fact, they are, rather than providing annotations, they need to really perform the surgery using something similar to a joystick. It's a wireless joystick. So they need to get used to that, and requires training, right? So that is an aspect of the work that needs to happen.
Did you factor that in at all? Because you have the graph showing the machine learning aspect of the training. Like, if you account for the training that the surgeons also need, how much of that time or investment do you think is split between like machine learning?
Yeah, it usually took a few hours to train the surgeons. So the graph that you see is actually when the surgeons are proficient with the system. Okay. Because otherwise, what you measure is not how fast the system is learning, but how the human is learning, which is a good question, but it's not. I mean, humans actually can learn. We are very good at learning. The problem is that robots are not as good as humans to learn, and that was the main challenge there. So now, okay, so we started with a setting where we have humans in the operating room working, and collaborating or working with robots and monitors, and then we took the robots and started them, and send them. No, and then we took the humans and we separate them and we kept one person locally and the other in a very remote location, and we use augmented reality and telecommunications to provide instruction. And then we removed the medic and we brought a robot and we saw, okay, how this robot can actually perform surgery. And now what we're going to do is we're going to remove communications. We're going to remove communications altogether. And the question is how we can provide instruction without communications. Okay, so that will be the question. So the concept was, can we actually take this mentor that we were using in the first project, but can we generate an artificial intelligent mentor? So the idea was, let's create a database of surgeries, of procedures that is huge, and let's caption the frames. The captions will be instructions of what is happening. Let's describe what is happening. Let's learn these captions, so when we see images that look exactly like those in the database, these captions are going to show up, and we can use, for example, natural language to convert that to speech. And those were going to be the instructions that we're going to provide to the medic. So these are some examples of it. Okay. So for example, tracheostomy. Here are the frames that we capture. Identify trachea with palpation, cartilage, identify cortical cartilage, tubular notch. All these things were the captions that we use. And those were the ones that were used for the machine learning to learn captions. So the idea then is you have the image, the caption is going to be generated automatically. And those will be the instructions. Of course, for this to work, you need a ton of images and procedures. So we look into step-by-step demonstrations, 290 different procedures, over 20 medical disciplines. Over 17,000 images we use. And in addition to that, we compile expert information from 5 medical facilities, and we included captions and images from academic textbooks. And all this is in the DAISY dataset, if you're interested. And it worked very well, with one exception, right? The exception is that recognizing what's going on right now is not helpful to tell the medic what he needs or she needs to do. So one thing that you want to do is to tell what needs to happen, not necessarily what is happening now. So what's happening now is important, but it's not useful to know what needs to happen. So we look into, and the other problem is you lose this ability of prediction in the moment that you don't really capture the history of the procedure. We're using actually here still images. So we say, okay, why don't we use actually a data set of videos? And let's break into these nice images of the operating room. We got into what is called the created the Thompson data set and Thompson challenge, which is, let's look into images and procedures that happen on the field. Let's collect them with as many variations as we can, as different as possible, performed by different people, different settings. And let's see if we can predict what activities need to happen, in fact, regardless even of the procedures. Even that we collected information from 5 different procedures, okay? So we look into 5 procedures: tube thoracostomy, crike, tourniquet, IO, and needle thoracostomy. And these are some typical sequences that you see, but you see that they're very different, one from the other. And we created the Trauma Thompson Challenge, which is right now is going to be featuring in MICAI 2023, in October 8, from October 8 to October 13, where what we are trying to do is do action recognition, action anticipation. Action anticipation is important because those are the instructions that an artificial mentor will give, task recognition, and visual question answering. This is also nice. We want to have the ability of asking questions, why we perform the procedure, and having the AI being able to reply. So,
action anticipation, recognition, etc. There is a number of resources like Epic Kitchens dataset
right,
that they have this challenge.
Exactly. This is a challenge very similar. I don't know what happened with the computer. Okay. Very similar. Give me 1 second. Oh gosh, I never had this happening. Very similar to the kitchen challenge, with the exception that rather than cooking, here what we need is treat casualties. I don't know what happened here. Give me 1 second. Okay. Yeah. I'm back to it. Okay. Crash. Okay, let's. Oh. So we took the model of the EPIC kitchen challenge and we said, okay, let's have a similar setting where we can recognize tasks, ask questions, and okay. What you see here, this will be good to, I think, to have a YouTube. This is nice, actually. That's why I think that, is there a way to connect maybe to?
You should be able to join EDU Rome.
But I don't see it here.
It was there a moment ago. Maybe go to other networks.
Because I don't think
other networks.
Yeah. Okay.
Just put your full Purdue email, and then your Purdue password.
This is my username, not email, right?
You need to put your full Purdue
email.
Email, yeah.
Okay. Let's see how well this works. Oh, it seems that it worked. Okay, I think that hopefully, I don't know. I thought that it was working. Now I'm not so sure. I think that I'm not really connected. It's connected. There's chess. What's going on here? Maybe it's not here. Okay. All right. So it's the video of the challenge.
Next step, take syringe. Take needle. Remove cap. Tighten strap. Twist windlass. Are you ready?
All right, so.
Have you annotated the data set?
Okay, so here's the interesting part. These procedures are annotated, and I'm going to explain how. But the idea is to do this without knowledge of what particular procedure I'm running this. In other words, the idea is to have enough diversity in the data, so regardless of the procedure that you perform, you will be able to recognize the actions in every frame. Okay, which was, again, a similar idea applied to the kitchen dataset. Regardless of what you want to cook, there are certain patterns that repeat regardless of what you're going to create. Here, the assumption is the same. which is a very different approach than the traditional one, where we say we know a prior, we have a prior, which is we know exactly what procedures we are running. Here, we don't know them, or we're going to assume, of course, we use a certain number of them, but we're going to assume that this will generalize to any procedure. And it's a challenge, and of course, for that, you need a lot of diverse data and a lot of videos. So we created an app to annotate the different actions, so you can see for a typical procedure how many annotation steps you need. So we actually created the app that allows you to stop and use natural language to tell what is the activity currently happening. As you see, every action is a combination of a verb and a noun. Okay, so it's a simplified version of what you need. We look at the distribution, of course, of the verbs and nouns. As you see, there are certain ones that are extremely common, while they're for other procedures or other actions, some of them are very, very unlikely to happen. And those are the more difficult because require more to learn. Another thing that we did is create knowledge graphs for the procedure. So can we represent the knowledge or what is happening in a way, in a compact form, that we will be able to show the medics, and visually they will know what they need to do, and we can use that information also to recognize procedures. So we created these task graphs that have a combination of nouns and verbs. So there are the actions, they have chronological order on the edges, and you can trace them and follow the whole procedure. So the idea is that for similar procedures, the knowledge graph looks similar, and for different ones, they are very different, right? Of course, you can use then matrices, adjacency matrices, and other types of representations to calculate distances between these graphs, similarity between graphs, right? And you can do a lot of cool stuff. For example, you can use different metrics like Mahalanobis metrics and PCA to recognize shortcuts. For example, in this case, a shortcut is a point, one of those points that are inside the cluster, and mistakes are those points that are outside the cluster. So these graphs, what we want to do, and we're still working on this, what we want to do is to be able to recognize typical procedures. We want to recognize mistakes. We want to recognize shortcuts. We want to recognize creativity. What is the meaning of that? We want to be able to evolve, have a way to evolve these graphs to see if we can create or find more efficient ways of completing procedures. So
the graphs, the nodes are objects and the edges are actions?
No, the nodes are nouns or verbs. You see, I use different colors.
Nouns or verbs.
Right, and the edges are actually the sequential order. Indicate the sequential order. So what happened after what actions, right? What actions happen after what?
This is a directed graph.
And it's a directed graph, but it's not acyclic because there are certain operations that are recurrent. Okay. So we have some tricks here. A traditional graph representation using adjacency metrics is not enough. You need to add another matrix that represent also the chronological order of the sequence. So we are, so of course, after the graph, we also need the algorithms for action recognition and for action anticipation, okay, using neural networks, we're using transformers in both cases. And the results, and you see here I'm bringing the kitchen that you asked. See, for the kitchen also was kind of difficult. That's why an open challenge. Epic Kitchen, you see that the best performer is 39% right now. In our case, the best performing the repeat is 18%. Okay? Now, we also look at the different procedures. Out of, the 5 procedures, some of them we actually do really well. If you look at the top 5, it's the most optimistic result. Top 5 means any answer out of the best 5 I'm going to accept. Top 1 is just the best answer, right? Which is the action, the combination, and the verb and the noun. So the combination is always much lower. You see that the performance is quite poor. And that's why it's an open challenge. I repeat, this is a challenge because you don't have prior knowledge about the procedure that is being performed. And you don't aim to recognize it. You only aim to recognize the step. The idea is to be able to recognize any procedure here. Okay, so we're very curious. Now, of course, if you're interested, take part in the challenge. It's still ongoing. And we're going to see, what are the results that we get. So these are some of the examples of action recognition and action anticipation for the different settings. This is interesting. This is I don't know if you can see anything. This is a dog simulator. So this is basically a tourniquet being performed on a dog. Now the image looks bad. Yes?
What happens if one local, tool or one group of doctors calls a tool one thing and a different group of doctors calls the same tool a different thing? Or you don't necessarily have that exact tool in your toolkit at the moment, but you have a very similar one that could work instead.
Okay, so two answers for two different questions. The first question is what happens when you don't have when you don't use the same terminology?
Yeah.
So what we do is we want to extend this. This is not currently working that way, but we want to use this with semantic trees that allows you to find neighbors on the graph where you have synonyms of a certain word. And that is considered, for the sake of it, a similar word. Okay, so we don't have that. For that, you really need access to these large language models, which is the next step. And that is one way to solve. The second question is very interesting. And this is the work that the next step on this data set is we want to bring this to the field, to field data, which is really totally contrary to the idea of a control setting on the operating room. What happens when it's uncontrolled? Not only that you don't control the light, the performer, the clothes or the field, but also you don't control. In fact, we want to apply this to extremely limited settings. So when the settings are limited, you may not even have the tools that you need. So you may need to improvise. The idea of this data set is to be able to allow you to perform tasks and give enough space, if you want, or enough generalization for this improvisation or these changes in emergency procedures. So we call that basically improvised procedures. When you are in a setting that there are no resources, there are austere settings, you have different tools, a limited tool set, or basically with that you need to deal with. Yes?
Is that previous slide a while back where you were talking, it listed visual question answering, is that tied into this at all? Or how was that being implemented?
Okay, this is him. You need to ask him about that. Visual question answering. Is the page triage? Is the patient breathing?
Yes. What was the question?
Just what the visual question answering means.
Well, you see the patient on the field. You may have a drone, and you want to know if the patient is breathing. It's moving, right? So how you can answer that question? Okay, so what you're doing is basically using robots and drones to be able to create signatures, I guess, of physiological information to be able to know what is the state of the patient in a contactless manner, right?
Yep.
So we're trying to do, in a way, a similar approach, only using computer vision at this point. In other words, we want to be able to, for these limited views that you have, be able to ask questions like, is the patient breathing? Is the patient moving?
Who is asking that? The robot?
No, this is a medic. Now we don't have a robot. Now this is a medic. This is a medic in the field. And there is an artificial intelligent mentor. He's not talking, there is no one else in the other side. He's wearing, for example, the HoloLens, and there is an AI agent. So now you want to be able to ask certain questions. One, I guess that you could regarding the question whether the patient is breathing or not, you could look at the patient and know, but there are certain questions that you may want to ask about the procedure that are not clear to you because, again, you're a trainee or you're a medic or you're a naive surgeon, right?
So the person asks a verbal question and the holograph
Yes.
helps them. Wow.
They are.
How does that work when you have a bunch of noise and well, I guess that's
Ooh,
kind
yeah.
of.
But there is a lot of noise. Again, here, imagine, again, going back to the silly example of the patient breathing, if you're not able to see the face or the throat of the patient or the chest, I mean, you need to rely on very few observations that you may have as the medic is moving to be able to come up to the conclusion or the answer.
Okay.
And, you know, in a way, if you have a drone or a robot that is hovering on the patient, I mean, you may have more information, but still it's going to be very challenging.
Yeah, I mean, I think
Right?
you can actually do quite a bit with an RGB video. There's actually, techniques. They're not machine learning based generally. They're more first principles, signal processing. But if you take a video of your face,
Frequency
actually
based.
an iPhone app that does this.
Yes.
You can get your heartbeat and your heart rate just from minute changes in your complexion that occur every heartbeat. So by analyzing the signal in the frequency domain, you can see very distinct features. So we're using RGB cameras. We're also using thermal cameras, and then we're using something called a depth camera. So a depth camera gives you basically an image that represents the distance to the surface that you're looking at. And so once again,
You can measure the chest movements.
The procedure that you use is you identify a control region on the surface, and then you can look at frequency perturbations relative to the control region, and that allows you to compensate for any fluctuations in the motion of the camera platform. But then you can discern things like respiration rate and heart rate.
Okay.
You can ask questions, more elaborated questions like, is the patient in pain? Right? And being able to assess the level of pain of the patient from images. So there's a lot of interesting stuff here that can be done.
Okay, so a lot of this is like implicit, like just from the camera being able to pick up various movements and color changes. It's not necessarily all just explicit question answer.
Well, you do need to provide annotations from videos that you collect, but the idea is that the model will be able to generalize well enough for new settings, new environments, new patients, and new conditions.
I think what you're getting at is the idea that in addition to the AI mentor, the individual performing the procedure could also be receiving information about the vital signs, which are obtained in real time through the same video feed. And in fact, the AI mentor's suggestions could be based in part on those vital
that
signs.
information.
And it all kind of improves the quality of care.
Right. Yes, definitely.
Medic also has to record what he's doing, to make notes in some way.
But the system could record. We don't have that. I mean, it's not the way that it's working right now, but the system, remember, you're using HoloLens. It could record the movement of your hands, record, of course, the patient, the state of the patient, everything.
And the other modality we're looking at, of course, is two-way audio. So because even a lot of the trauma mannequins have the ability to make noise.
Speak, yes. In fact, the new ones can actually, part of the training is they actually can scream. Yeah. You can actually talk to them and say, "Are you okay, buddy?" And they will answer. Yeah. And it's part of the training. So
I'm gonna just point out that we started 5 minutes late, but we only have maybe 5 minutes left if we stick with our normally scheduled time. So Dr. Wachs definitely has the floor. It's totally up to you what you want to use the time for. You knew that this
you
was
just
coming
said,
next week.
yes, I knew. That's why I went loose.
I wasn't sure how much longer we had.
No, I went. So, some final thoughts. We're going to conclude, I think, with this. Human element is not only essential, but it's a strength if we know how to use it, which is what this research is about, and these questions is about. How we project human interactions and human actions from a source domain to a target domain, from a control setting to an uncontrolled setting, is this idea of providing not just telepresence, but active telepresence. Domain knowledge can be learned. One approach, which is the brute force, quantities of data, tons of data, and hope that the model learns. Better than that is have a user provide feedback about what is useful and what's not. Okay, what is the domain expertise? What we look is the domain expertise. And again, we rely on the fact that human intuition is very relevant to solve these problems. Okay, of course, human intuition is not pure intuition. It's based on knowledge and based on years of personal experience and community experience, right? That is what we call context, and is the key part of the modeling of these AI systems that needs to be considered. All right, I want to acknowledge my sponsors, and these are some of the students and collaborators that work in the project. There is a bunch that are not here, but yes, still I owe them many thanks. So with this, thank you very much. Yes, please. Sorry.
So I had one question. Where,
yes.
The person who is operating the human via the AI agent does a mistake accidentally, and then can the AI agent supervise him still to correct it? Right
now it's not the objective of the challenge, but the graphs that we're creating are allowing us to tell whether what you're doing different is more effective, and therefore we are going to either encourage you or leave you alone, or if you diverge from the prototypical graph, knowledge graph, we are going to actually let you know that you are making a mistake. That's where the knowledge graphs are used for.
One last question. Like, this is all based on vision. So
correct.
You said in uncontrolled environments. So what if smoke is there? Smoke.
What is what?
Smoke.
Yes.
Presence of smoke will affect.
Presence of smoke is going to affect computer vision, definitely, and the number of, and if the environment is dark, it's going to affect, and there is a number of factors that are going to affect the system. So how robust the system will be under those conditions? Yes, the system is going to be affected. And when I talk about uncontrolled conditions, I'm not necessarily emphasizing that side, which is also can happen, but I'm looking at different environment, not operating room, a tent, a field, a grass field, a dirt field, I don't know, a mountain, a cave, or the cave is going to be dark, but a variety of environments, a variety of people, variety of procedures, variety of tools. And I believe what you are saying, it's very helpful. I think that in the next iteration of the challenge, what we can add is these stressors that are realistic for the Department of Defense, which are smoke, explosions, darkness. Of course, we'll have to rely on other modalities, right? If you have complete darkness, the color setting will not be able to help. We'll have to go into other channels, other modalities like thermal, infrared imaging, and so on and so forth.
Sorry for one last.
No.
I think actually I'm going to say we should thank the speaker, but please, he has a little bit of time
sure.
until this next week, so you can definitely chat one-on-one afterwards, and anybody else that wants to chat one-on-one afterwards also. But I'm not sure if anybody has the room after us, so let's thank the speaker one more time. Thank you very much.
Thank you.